Okay, here we are in the visual acuity part 5, and we're still talking about factors. And definitely today, the main topic will be Nyquist resolution limit and other factors too. So let's move. Sometimes it's very important to talk about whenever we are talking about visual acuity, it's media, isn't it? Sometimes cataract, corneal opacity, and definitely they will affect. And sometimes disease in the retina, obviously, they affect. And the main role is pinhole effect. And as we have discussed in previous 2 or 3 videos, that when people get smaller and smaller, diffraction increases. When people get larger and larger, what do you call that, aberration increases. But at the same time, we have to discuss about if pinhole effect comes because of a small pupil. So there are two things. Diffraction increases, yes, but at the same time, depth of focus increases. Okay, if depth of focus increases, then we can slightly shift object position, but without changing resolution in our retina. So that's one benefit of pinhole effect. Okay, so pinhole effect creates a benefit, at the same times creates a problem. Because what type of problem? It creates diffraction and blur effect. So we have to understand in visual acuity, especially visual acuity at near, isn't it? So whenever you are going to do visual acuity for what a presbyopic patient for near, then you have to understand the concept of depth of focus, and at the same time relation with the size of the pupil. Because many times for distance it affects less, but for near it affects huge. Because for near, depth of focus matters, and whenever you are going to prescribe in case of bifocal, trifocal, or progressive, at that case, particular case, it's very important to realize that people can work as a pinhole, and depth of focus increases. That's why you need very small amount of add, or you have to reduce the power of add. Okay, so that's the key point here because of pinhole effect. Okay, then we are moving towards the most important point, that is definitely the dimension of retinal mosaic, or retinal, definitely mosaic means the mosaic pattern of cells, and the digital limit. So the basic concept here is dark and white part stripes is given, and such a gratings can be resolved. That stripes like this red and white, red and white, red and white, red and background is white. That's why red and white, red and this stripe. That's why black and white is stripe is given. So there are a row of unstimulated cones between the stimulated cone. Means one cone is stimulated, one cone is unstimulated, one cone is stimulated. Stimulated, unstimulated, stimulated means no, yes, no response. Okay, so it means yes, no, yes response, whatever. Because this is stimulated, this is not stimulated, and this is stimulated. If at least one cone is unstimulated, then it can be resolved, and that's the concept. Here's the picture. The row of hexagonal cone cells, and the average spacing is this. Okay, this I will show you in another video. It's better remembering this. The space between in fovea, the space is 2.6 micrometer, which definitely approximately correspond to 0.5 arc minute. You can convert it, isn't it? Can you convert it this value? So you can convert this value by calculating. Okay, what is the angle made by this particular 2.6 micrometer? That's your work, it's a homework. Okay, so it approximately corresponds to 0.5 substantial nodal point, and you know that nodal point between retina to secondary nodal point, it's approximately 17 mm distance. Okay, and then you can calculate this 2.6 micrometer, 17 mm here. Just calculate the angle. Okay, it's quite okay. But two of the cone are stimulated and one is not stimulated. This is the perfect criteria for resolution. So foveal mosaic geometric pattern, and that's what. And this is the study. Just all the study shows approximately 2.6 micrometer is good spacing. At least 2.6 micrometer means one diameter of the foveal cone, isn't it? Because one is stimulated, one is unstimulated, and another is stimulated. Okay, so that's why in case of neural signaling, okay, neural signalings, or whatever we call retinal theory or Nyquist theory, so we consider 0.5 arc meter, arc minute is a resolution capacity, which is directly corresponding to 60 cycles of minute. One arc minute is equal to 30 cycles per degree, isn't it? Okay, so this is the case of 20/20 vision. In case of left This is 2020, and this is 20 by 10. So 20 by 10, you can see only one spacing, only one cone. 20 by 2, you can say more than one, isn't it? The space between, these are the space between black and white. So these things you must understand. Okay, a retinal mosaic cone spacing, one cone is diameter is 2.6, and that corresponding to 0.5 arc meter, which means eventually 60 cycles per degree, isn't it? So sampling by cone set of limitation, a pair of illuminated cone separated by single unilluminated cone. That's very important. One is illuminated, unilluminated, and again illuminated, and this case creates resolution. So that's the case. Okay, so what I wanted to tell you in the Nyquist, uh, basically Nyquist limitations is it tells us that at least one cone must be unstimulated between two stimulated cone. Okay, are you getting the concept? At least one unstimulated cone must be there, unstimulated between two stimulated cone. Okay, and the unstimulated cone has diameter of 2.6 micrometer, and whenever you convert that 2.6 micrometer to angle with a nodal point, how will you convert? I already told you. If this is a, this is cone, okay, nodal point is secondary nodal point, and distance between secondary nodal point is, let's consider 17 mm. We normally consider 17 mm, and the angle formed between this cone, which is 2.6 micrometer, and 17 mm. Can you calculate it? It's very simple, isn't it? 2.6 micrometer, and just make it 17 mm to micrometer, and whatever you get radian, because theta is equal to sine theta is equal to tan theta, when theta in radian is a small angle approximation, isn't it? Sorry for my handwriting, I'm so sorry. Okay, that's the part fifth. Okay, I want to tell you in the Nyquist theory, which is very important theory you have to understand, because it's a neural theory. Sometimes it's connected with neural theory, sometimes it's connected with the retinal optics or retinal resolution optics. I don't know, there are a lot of terms, but you have to understand two theory. One is the diffraction, and then which eventually corresponds to the Rayleigh um, criteria for resolution, and the Nyquist theorem for resolution. So both of things comes here. And Rayleigh's criteria, what it tells us, Rayleigh criteria, it tells us it's 30 cycles per degree. It's 1 minute of arc, but what Nyquist theory tells, it's 0.5 minutes or 60 seconds of arc. Just remember these things. It's important whenever a faculty to can ask you an exam, or it will really, people will really understand how deeply you understand visual acuity from these concepts. Okay, central important. That's why I'm going to make, I think, 10 parts of visual acuity. Okay, till Bistan, choose. And this is my favorite book all time, Professor Dr. George Asimali. This is the reference. Just pick that book and read. Okay, okay, fine, choose.